Discussion panel yesterday, I was very pleased to see that control was highlighted as the key problem. And if you see here the logo of my group, control is something that's very important to us. And you also see the essence of what we understand under control. So you see the Berlin TV tower in a non-classical superposition. And it has been brought into this non-classical superposition by using controls, so external fields that are shaped in a specific way. I also thought, however, that probably I'm giving the wrong talk, because I'm not going to talk about control, even though we published a series of papers on minimizing resources a few years ago. But I didn't decide to change my talk. I figured that the industry people would be gone by today, and with a notable exception, they are. So I'm free, enjoying my academic freedom, and can rather talk to you about something that I'm much more excited about, and even if just because it's what we're doing right now, as I think many of you can sympathize with. So, what does it take to cool a many-body system? First of all, even if this is a bit lame, maybe, let me tell you that this is a really hot topic. So this is a Google search I did a year ago, and it brought up about 6,000 results, and most of them from the past 2 years. And the reason is that, well, let's answer the question in 2 steps, really, right? So we have, why do we want to cool? Well, this is pretty obvious to everybody immediately, I think, because this is where quantum comes to appear, where we have coherence and we can leverage quantum properties to do something fun or useful. And then why many-body? And one answer is because this is already about doing useful things in the sense of cooling to a many-body system to its ground state, like in this paper from the Google group 2 years ago, is equivalent to doing a quantum computation, or can be equivalent to doing a quantum computation, because you can prepare in this way ground states of many-body Hamiltonians, like in their case a 2D transverse field Ising model, and I think they had a few other models in that paper as well, that encode the solution of a computational problem. So that's kind of its own approach to quantum computing or quantum simulation. Many-body systems are also important for quantum sensing, because then you can leverage interactions and entanglement for quantum advantage and sensing. So many-body quantum probes in their thermal and steady states play a key role for such quantum-enhanced sensing protocols. Okay, but one point which I think is absolutely underappreciated is that in these scenarios, the target state is typically not known by definition, because we're looking at complex systems. If we could write down the ground state, it wouldn't be so interesting in the first place. So when we talk about cooling many-body quantum systems, what we want, ideally, is something that works universally, which means that it should work without me having knowledge about the quantum system, without me tailoring the cooling protocol to the properties of the quantum system. Okay, so then, under these premises, what does it take to cool a many-body quantum system? The short answer is a cold bath. Okay, sounds trivial, but it's not, and the reason it is not is because having a cold bath at your disposal, you can come up with cooling protocols that require essentially no knowledge of the many-body quantum system. And because this is non-trivial, I will give you the long answer in this talk. But before doing this, let me highlight the people who have contributed So it's quite a large team. Josias Langbein just graduated a month ago from my group. George Mouloudakis is a postdoc in my group. Emma King is a student of my longtime, very dear collaborator, Giovanna Morigi. Steve Campbell was a visitor to Berlin 2 summers ago and has been actively involved ever since. And all of this grew out of quite heated discussions with 2 condensed matter colleagues, Igor Gorny and Yuval Geffen. Okay, so let me give you the long answer. And let me first walk you through what are the specific challenges that we will need to address if we want to come up with successful cooling protocols. So even if we don't know the spectrum, we know that it is rather complex, meaning that there are many different transition frequencies, maybe even of different orders of magnitude. And since we don't know where excitations are hiding, we may need to address all of them. Second, we may have symmetry-protected subspaces, and if we don't address this, then we will pump, or we may pump population into these subspaces, or at least not be able to get excitations out of these subspaces. And these symmetries may not necessarily be known to us if the system is sufficiently complex. And of course, then another hallmark of many-body systems is frustration, which means that we have competing terms that we cannot cool, so cooling locally will not work. And also steering, so I'll introduce what I mean by steering, will not work in this case. Okay, so our approach to cooling is to see it as an instance of quantum reservoir engineering. And let me remind you what we mean by this. So we have a system which is described by its Hamiltonian, and in addition, it is subject to dissipation. And in quantum reservoir engineering, you want to drive the system into its steady state, and you want to choose controls on your Hamiltonian, on your system, such that this steady state is non-trivial. Maybe just pure, maybe it has some more interesting resourceful properties. Let me start with a simple example. So I come from AMO physics, and I always like to understand processes with AMO physics. So here's an experimental implementation of quantum reservoir engineering that works almost. It's an experiment from the trapped ion group at NIST, where the target was to drive these 2 red ions, these are beryllium ions, into a maximally entangled state, a belt state. And the complexity of quantum reservoir engineering already shows up at this level if you really think about all the physical processes that are relevant, because they didn't need 1 field or 2 fields, they needed 4 external controls to drive these 2 ions into a belt state defined on the qubit subspace. So this level scheme is the essential model for a single beryllium ion, hyperfine qubit, an additional auxiliary state. And then we have an electronically excited state, which is very short-lived. So this brings in the dissipation that we want to leverage to cool. So we have a so-called repump laser that excites to this excited state, and then the spontaneous emission brings us back to the ground state. The ions interact because of the Coulomb interaction, and they vibrate in the trap with shared normal modes, and these you can address using a sideband laser that changes the vibrational excitation in the trap. And then they needed laser cooling to cool the vibrational motion in the trap, and this is why you see these 2 green ions in the middle, which are the magnesium ions, which are laser cooled. And I said this works almost because the dashed line here corresponds to what they did in their experiment. And you see it leverages off at about 75%. Now we thought this is a nice control problem. Let's optimize the polarizations. Maybe they didn't think about this. And indeed, you can push the 75 up to 90%, but then you really hit a hot wall. And the reason for this is captured in this picture on the right, where we visualize the state space of the 2 ions and the vibrational motion which goes outside for excitation. And you see all these lines here correspond to the 4 different fields. And the target state is the one in green here, and you see that the black line representing the microwave drive actually outcouples this state to another state. So in their implementation, the target state was not identical to the steady state of the Derwent dissipative evolution. Okay, so then we said, oh, let's again use our machinery of control theory and not just look for the best parameters, but let's look for the best choices of drives. And the answer to this optimization was that we should keep the repump, obviously, because this is the dissipation that we want, and the blue sideband. We choose a different microwave transition, also obviously, because this is what was causing the trouble. And we found that we can replace the laser cooling on the magnesium by a red sideband laser that decreases the vibrational motion, but doesn't cool. And then, of course, we optimized the Rabi frequencies and detunings of these fields. And indeed, then we get a scheme where we have no transitions out of the target state. And the error, if we just wait long enough, we will pump the system into the Bell state. And the only remaining source of error is what is not included in our model, so-called anomalous heating of ions in the ion trap. Now, when we came up with this solution, the people at NIST got super excited for a reason which I didn't anticipate at all. But maybe it's in line with the theme of this conference of thinking about resources. They were super excited by the fact that you can replace the laser cooling on the magnesium ions by another laser. Because that means they can do the experiments with just 2 ions in the trap instead of 4. And that's what they did. So here's the experimental implementation of our protocol with now just 2 ions, and instead a red sideband laser in addition to the blue one. And their best result was about 95% fidelity compared to the 75% they had before. So not yet 100, but they did a very careful analysis of the error sources and concluded that if they could increase their Lambda-Dicke parameter, I won't go into the technical details, they should push down this error further. And by that time, they asked me another question which I didn't anticipate and which I would not have thought about myself, and that is, we made very sure in our calculations to not exceed the laser power that they had used in their original experiment in 2013. Because this is a UV laser, UV lasers are quite hard to operate and to limit it in the amplitudes that you can get. So, but then Didi Leibfried asked me, so let's assume I have a power budget that is very large, maybe even unlimited. How much laser power would I need in order to reach the error correction threshold, in order to prepare my state with a fidelity of 4 nines? And this is the answer. It depends on the heating rate. So if you have a heating rate of 10 hertz, you're never going to go close to the 4 nines, which is this threshold here. If you have a heating rate of 1 hertz, so on the time scale it takes you to prepare your Bell state, you're still not going to get close to 10 to the minus 4, but you're already at the order of 10 to the minus 3. You really need to make sure that you manage the heating of your ion trap during the preparation of the state such that it can be essentially 0. And they told me that's actually feasible. And then it takes this much beam amplitude or beam power, or if you're smart, because now you have 2 Raman transitions and you can combine the 4 beams of 2 Raman transitions into 3, you can move it down there. Okay, but let's come back to the bigger picture of quantum reservoir engineering. The key point of this example is that here we have used natural dissipation, namely spontaneous emission from this highly excited electronically excited state. And quantum reservoir engineering for many body systems is not a new story. It has already been discussed theoretically almost 20 years ago with many, many papers telling us how you can use these processes to prepare really non-trivial many-body states. And back in the time, I was extremely skeptical because, I mean, this is beautiful theoretical work, but they always assume that you can have jump operators, dissipators, which are at least 3, 4, 5 body. Well, these just don't exist in nature, right? Our spontaneous emission is a one-body process, by and large. So if you want to do this with natural dissipation, you know, you may get leakage. This was the reason why you need so many fields in the ion example. Or it may just not be available, and typically it is local. So then, what about these proposals? Should we throw them out of the window? Well, there has been a more recent development in the past maybe 4 or 5 years, and this is the field of measurement-induced dynamics. So formally, measurement and dissipation are completely analogous, and that also means that you can engineer dissipation via measurements. Or even more broadly, you can couple your system to auxiliary degrees of freedom, trace them out, and that also creates the desired dissipation. So let me explain how this can be leveraged for the preparation of many-body states with the example of the so-called AKLT state. So the AKLT model is a condensed matter model named after its inventors, Affleck, Kennedy, Leib, and Tasaki. And it has several interesting properties. So it's a spin, it's a chain of spin 1 particles with periodic boundary conditions as visualized here. And its Hamiltonian can be expressed in terms of these projectors that operate always on a link, so on 2 neighboring sides of the chain. And is of this form that it contains these projectors. So it's non-local, but only quasi-local because it couples only next neighbors. It's frustration-free, but yet the Hamiltonian is terms are non-commuting, so you get an interesting many-body state in the sense that the ground state is a topological state, it's a so-called valence bond state, so a sort of superposition of a singlet and a triplet between the different sites. If you have periodic boundary conditions, it's non-degenerate and it's unique. So that makes it suitable for driven dissipative evolution because you're guaranteed, if you make it the ground state, to really go into this, make it the steady state, you go into this state. And my colleagues, Igor and Yuval, they had come up with a way to steer into this state by saying, let's even forget about the Hamiltonian. Let's just attach to each of these links meter qubits in such a way that the interaction with these meter qubits realizes these jump operators. And you see that these jump operators de-excite all the states with j equals 0, so all the excited states. And then you can, if you just let the system interact with these meter qubits for a short time, trace them out, interact, and so on, you do approach the steady state, the target state, the ground state of the AKLT. Okay, but there's a catch, and that is you need an extensive number of detector qubits, right? You're attaching to each link, you're attaching 5 meters. So it scales with the number of system sites. And that's not very resourceful either. And in the meantime, there has been another proposal to prepare this AKLT state by Wiebe and Gerwin and collaborators. And also in their case, the number of measurements is extensive in system size. What we found, a bit to our surprise, is that actually it's sufficient to cool a single link. So in this case, you need the Hamiltonian, you need the coupling between the different sides, but then you can just attach meter qubits to a single link, and you see you can still approach the ground state. How fast, that depends on the spectral gap of your Liouvillean, and the spectral gap, of course, decreases as you increase the system, but it does so algebraically, not exponentially. Okay, so this is scalable. So why does it work? Well, now look at the target state, the AKLT state, but just reduced to the link that you cool. And then you see that you get a partitioning of the state space into the hot subspace, where all the excitations live, and the cold subspace. So the meter qubits take you from the hot to the cold subspace by design, sure. But the beauty of the AKLT model, and where we got sort of lucky, is that if you now go back to the many-body picture, all the many-body states have a non-zero overlap with the hot subspace. And that means the part of the many-body state that resides on the cooled link is cooled, and then the interactions let the remaining excitations propagate to the cooled link, and then they are pumped out of the system by this local refrigerator. And in the case of the AKLT, this worked out of the box naturally, but understanding this picture also taught us what to do if it doesn't work out of the box, because then we can look at quasi-local operators that preserve the target state. And these are states, so this is what we call the kernelizer, or the space of the operators, of these quasi-local operators that don't re-excite our ground state. And we can add these to our Hamiltonian if the excitations are not propagated by themselves to the cooled link. So this scheme works for any frustration-free quasi-local Hamiltonian, and in the paper we work out the math, the algebra, explaining this, and also provide another example. So the achievement so far is we have finite cooling times for finite systems. It works provided we have this partitioning of the state space into hot and cold, which corresponds to frustration-free quasi-local Hamiltonians, but also PEPs. In essence, whenever you can well describe a system by an MPS, then you can use this cooling protocol. But it requires engineering of still three-body interactions. So not 4 or 5, but not just 2. So I would say, yeah.
I don't know if now's a good time. I didn't quite catch this measuring system is a qubit coupled to a macroscopic measurement apparatus, or?
So it doesn't matter. That's why we called it blind steering. Okay. So we don't read out the measurement result. It's really just an auxiliary degree of freedom.
And just one qubit is enough, because I think you maybe need to get hot.
No, sorry if I wasn't clear about this. Exactly, no, so you couple to one link a qubit which has been prepared in its ground state, then you, after some interaction time, you disregard, you couple, no, you disregard. Or you reset by measuring. I mean, this is...
I think in some communities it's called a collisional model.
Exactly, I'll come back to this point.
Yeah.
Because at this point what I wanted to highlight is that there are 2 limitations. Okay, one is it works for a broad class of Hamiltonians, which is interesting, but not for every system, so it's not universal. And it requires three-body interactions, which are non-trivial to engineer if you really talk to experimentalists. So we asked ourselves, can we simplify this and at the same time make it more generic? Okay? Or in other words, can we design a cooling process that is truly system agnostic? And here's now where comes this picture with the collision model. So this is the idea that we have in reservoir engineering. And indeed, the overall framework is this. We have a quantum system. It can be a chain, it can be more complex. And we are coupling meter degrees of freedom, which we are able to prepare in their ground state, so they're cold. We let them interact with the system with the interaction strength gamma for a certain time, and then we disregard them. Okay, yes. So this is an instantiation of a collision model. Okay, and surprisingly, I mean, of course, we're not the only ones thinking about cooling and using this picture of the collision model, and there are really a lot of protocols. I just listed a few here. So quantum digital cooling, quasi-particle cooling, algorithmic cooling, sympathetic cooling, single ancilla ground state preparation, and I probably overlooked a few more. What was striking to us was that the one I listed here on the top, they actually speak about mimicking a natural bath. But yet, none of these protocols is truly system agnostic, because even though they see the analogy with a natural bath, in the end, they tailor their schedule, the way they make the meters interact with the system, very much to the system properties, to the spectrum of the system. And a natural bath, doesn't know about the system. You have a natural bath, you put the system you want to cool in it, and it cools. So this made us think, what does it really mean to mimic a natural bath? And let me again remind you of the challenges that we will have to address in order to successfully cool a many-body system. The solution should be mimicking a natural bath. So what will allow us not to know anything in nature? If you don't know anything, you have to randomize. Okay? So the solution is that we choose these couplings and the meter splittings stochastically. And then we need many realizations. So I'm not claiming what we do is the most efficient way to cool, but it is the most system agnostic way to cool. But even if you do this, so you're not making any assumption on the system, but now you have these interactions between the system sides and your meters. Some of these interactions will lead to heating and not cooling. How do you make sure that the cooling wins over the heating? And the answer is, effectively, you need to implement a rotating wave approximation. And this is possible if you choose weak couplings and long interaction times. And I'll get to what this means, not making an assumption on the system, later on. So this protocol is slow and expensive, but fully system agnostic. Okay, so let me explain in more detail how we mimic a natural bath, or what exactly it means to know the system. So there are two points to this answer. One is the spectrum, but the spectrum itself, you would think, is enough, but the spectrum is always defined with respect to a quantization axis. And when you couple the system to external degrees of freedom, like meters, the quantization axis also matters. So let's look at the most simple example that we can come up with, because there we can solve everything analytically. A two-level system and a two-level meter. Okay, so we have the system gap and the meter splitting, and if we choose their interaction in this way, sigma plus, sigma minus, then the protocol goes as follows. Our system is in an arbitrary state. The meter is initialized in the ground state, so the total state is this product state when we make the meter interact with the system. Then we have the time evolution under the total Hamiltonian, and after the interaction time is over, we discard the meter. And for this simple system, we can find the energy of the system alone, which is given by the initial energy minus this term. Okay, so this looks great. It looks great as long as the sign of your gap is positive. And indeed, if the sign of your gap is negative, you increase the energy of the system instead of decreasing it. Okay, and that's the sign of the gap is the quantization axis. Okay, so then what do we need to do if the gap is negative, well, then we need, instead of choosing sigma plus, sigma minus, we need to choose sigma minus, sigma minus, sigma plus, sigma plus. Okay, but we don't want to know, or we don't want to need to know the sign of the gap. So a system agnostic interaction would be a coupling of the form XX, because this contains both of these terms. Maybe now you see where the rotating wave approximation comes in. Because if the gap is positive, then this is the term that survives in the rotating wave approximation. If the gap is negative, this is the term. So these are, for positive gap, these are the counter-rotating terms, and vice versa for negative gap. So coming from quantum optics, we know what are the conditions for the rotating wave approximation to hold. We have to be close to resonance, weak coupling, and large interaction times. So how can we ensure this in this cooling protocol? Well, it turns out that for weak coupling, it holds automatically for almost all interaction times, except a few resonances that are of measure 0. Okay, so you're almost always guaranteed, if you pick a long interaction time, that the interaction time is good. Moreover, if you look at the scale here in red, you see that this is logarithmic. So the cooling rate on resonance for resonant meters exceeds the heating rate for the off-resonant meters that could potentially lead to heating, exceeds this by several orders of magnitude. So this is why we win. And now we can model this really in a system agnostic way. So we don't know the direction of our quantization axis. We capture this by this vector v. And then we want to randomize the type of interaction. Because also saying the interaction is XX assumes that the quantization axis is Z. But if we really don't know it, well, we can still choose here the interaction as a function of the angles of the sigma vector theta and phi and randomize over them. We can treat this interaction as a dynamical map and average it over the Bloch sphere and uniformly over the meter splittings, and calculate the steady state energy, and this is the result. So the steady state energy is proportional to the coupling and the inverse interaction time, which is why you need small coupling and large Tm. And this is going to work universally because of this randomly chosen interactions. So here indeed, this is the same story now visualized by numerics. Here we have the coupling, here we have the interaction. If the coupling gets very weak and the interaction gets very long, you can get this close to the ground state as you wish. Let me highlight the role of the system knowledge once more. So if you know everything, you know both the sign of the gap and the quantization axis, then you can choose the interaction to be plus minus and the meter resonant, and you will cool according to the blue line. Super efficient, but you know everything. If you only know the quantization axis, then you know that your interaction should be of XX. You don't know the sign of the gap. Okay. So then you have this orange line, and if you know neither the sign of the gap nor the quantization axis, then you need to average over the interaction directions, and you get the green line. So you do cool, and here your leverage off determined by gamma, by the coupling. So with this 2-qubit example, we understand the dynamics, we understand why it works, but maybe we are overlooking something, right? Because many-body systems are more complex than just a qubit. So here's now a generic many-body example, and anisotropic Heisenberg chain with this Hamiltonian. Our meters still have the splitting delta, and we average the interactions, and we average these meter splittings. And we compare to the same steady state estimate that goes with gamma and and 1 over the interaction time. And the plot looks really the same as for the qubit example. So let me remind you, I made very strongly these 3 points. What are the challenges in cooling many-body systems? So why can we address these challenges, or how are we addressing these challenges? Well, number one, we are not picking a single frequency, right? We randomly choose these splittings from a box, for example, and to this end, we need to know, or we should have maybe an estimate of the overall spectral radius, the energy scale of the system. Even this is not crucial, I'll come back to it. But it means we have many frequencies in our protocol, and we will cool when we pick a resonant one, and otherwise we will waste an interaction. Because we have a coupling, a local coupling to a meter, just two-body interactions, okay? If our system has symmetries, this is a quasi-local perturbation that breaks the symmetry. In case of the Heisenberg, it's the total spin symmetry which is broken. Moreover, we can cool frustrated systems, and again, the example was chosen to be a frustrated system because we get an effectively non-local interaction because we have both the interaction with the meter and the interactions within the system. And that's the reason why we need these large interaction times, so that both timescales can come into play. Okay, so how does it actually work, or how would one implement this in an experiment? Because I said I don't want to know anything about the system. It means I also don't know when my coupling is actually weak, right? Because that is weak compared to the gap of the system, and I don't know the gap. So what do? I make a guess, and I check if it converges. If my coupling is too strong, I don't converge. If it is weak, the energy converges, but not only the energy, also the energy variance. So I can check on the fly whether I'm cooling or not. And then how crucial is this estimate of the spectral radius? It's not crucial. If I have a good estimate of the spectral radius, then I can adjust the size of my box and it will be more efficient. So if I have a large box, you see it takes longer to cool than if I have a box which fits the frequencies better. But even in the case if I don't have a good estimate of the spectral radius, I can use a Gaussian distribution instead of a flat distribution, and that ensures that in the tails I will have all the frequencies that I need. And this is the two examples of the orange lines here. Okay, so once the interaction time is large enough, we get the same scaling irrespective of system size. That's quite gratifying and promising. And what this figure also shows you is the steering that I discussed for the AKLT doesn't work for a frustrated system. So for frustrated systems, you hit the so-called glass floor, and these are these dashed lines here, whereas with our agnostic protocol, we can decrease the energy. How does the cooling time scale with system size? Here we don't have comprehensive results. We have numerical evidence. So in the case of the Heisenberg chain, it seems to be independent of system size, but this is not true in general. Okay, and we are working on trying to figure out what system properties determine the cooling time. It's really universal. So it doesn't just work for this special Heisenberg instance. We looked at many systems. So here is an Ising chain with next and nearest next neighbor interactions. We looked at anisotropic XY model, XXZ model, Majumdar-Ghosh model. We looked not only on spin chains, but also on 2D configuration. So this is, again, this transverse field Ising model in those configurations. So we started to talk to people, and whenever somebody came up with an example where they thought, I think this is really hard to cool, we tried it, and we couldn't find an example where our protocol doesn't work. Okay. So we believe that our claim of universality is justified. Now, in the last part, let me now use this idea and see what we can do with it. And our original motivation had been, can we cool in order to speed up annealing? Okay, you know that in annealing you need to wait forever in order to reach the final state. What if we want to do it faster? We will get diabatic errors, but if we can cool these errors away, we are fine. So here's the idea of annealing. We start with a simple Hamiltonian and want to go to an interesting Hamiltonian, and we have a switching function. Can be this schedule, can be any other. And the idea is, let's assume you have a bad annealer such that this adiabaticity condition is violated, then the true ground state that you would want to follow as a function of time is the dashed one, and the one that you do follow is the green one. But if you add on top of the interaction and the schedule of the adiabatic model, this cooling protocol, you see that you cool to the ground state. And this works, again, not just for one example, but we have here also the Heisenberg chain. And indeed, this is what you can do now, irrespective of the initial state, right? So in adiabatic in annealing schedules, typically you start with non-interacting qubits, and then you can go to, let's say, a paramagnetic easing model, or you can go from a critical easing to a ferromagnetic easing, from a Heisenberg to a Majumdar-Ghosh, from non-interacting to Heisenberg. It doesn't matter. But then, in the end, you ask yourself, is there any advantage in running the annealing schedule at all? And the answer is no. And this is indeed also, they don't make the argument in this paper, but it is the philosophy of this paper that you just cool into the state that you want instead of bothering to implement an annealing schedule. And so this is the experiment. The theory was done by Abanin and his group. And what we do is related in spirit, but our protocol is much, much simpler and doesn't make use of the system spectrum. Okay, so let me wrap up and summarize what it takes to cool a many-body quantum system. So we want to mimic a natural bath, a cold bath. But in order to mimic not just a cold bath, but really a natural bath, it means we need stochastic quantum reservoir engineering. Still, you may ask yourself, maybe this is a bit too good to be true. No, it's not. But there is a price to pay, right? So first of all, your interaction times have to be sufficiently long in order to make sure that the steady state of this iterated dynamical map really becomes the ground state that you're looking after. Plus, on top of this, of course, you have the stochastic convergence. So in our numerical experience, it takes about 100 to 1,000 resets, depending a bit on the estimate of the spectral radius. But then, our steady state energy is proportional to the coupling and the inverse interaction time, which means that any system can be cooled into its ground state with arbitrary precision as long as these two conditions are fulfilled, where delta is a typical transition energy, like the gap of your many-body system. But even if your gamma is too strong, okay, or if your ground state is degenerate maybe, you're still decreasing the energy. It's just that you no longer resolve the ground state, but you're still taking energy out of the system. Okay, and with this I summarize. So I showed you that we should think of cooling as quantum reservoir engineering, really in the quantum engineering perspective, starting with this small scale example of trapped ions, where by choosing the proper external fields, we could ensure that the target state really is equal to the steady state. And then I discussed extensions to many-body systems, where we looked at blind steering, which works only for specific Hamiltonians, but if it works, it's super efficient. And if you don't have these properties, then you can devise a system-agnostic cooling protocol by having a sort of a stochastic collision model where you randomize both the meter splittings and the interactions. Key point, this is super simple because we really just want two-body interactions between our system sites and our meter qubits. But it's not fast. Okay. Let me remind you again of the team who did this work. And with this, I thank you for your attention.
Okay, so we have a bit of time for questions. So I personally, for personal reasons, really enjoyed the talk, not only because I was a postdoc with you, Geffen, a long time ago.
I didn't know that.
No, I realized I didn't get to chat before your talk. So I'm going to start by asking or making maybe a question or a comment, I don't know. So I think you might be being too modest, right? Because natural baths are not good at cooling many-body systems, right? They had many kinds of many-body systems have glassy dynamics. You end up if you calculate it just to a natural bath, it ends up in a local minimum and not the global minimum. And for me, that was why I always thought annealing was to try and get around that, right? You start in a simple Hamiltonian, in the real minimum of a simple Hamiltonian, and you avoid all of these local minimum and you go straight to the global minimum. But it seems like maybe building this kind of special kind of engineered environment actually is maybe better than a natural environment because it might help you avoid all of these local minima and get you straight to the global minimum.
But why? So
well, that's my question then. Okay,
thank you.
Is that true or is that me being too optimistic?
Thank you for the flowers, but so I'm afraid I'm not too modest because nothing comes for free, right? So how do we make this to work? And the catch is in here, right? So why does a natural bath not always work? Because a natural bath cannot adjust the coupling. Okay, so we say, okay, we can adjust the coupling, but we have to figure out what is a really weak coupling, and to this end we need to measure. To really determine the energy and the variance, and that is not for free at all.
Okay, I'm still not so. Let's discuss afterwards. I'm not so pessimistic. But so please, now I'll stop, and now I'll be a proper chairperson and ask for questions.
Thank you for the talk. Maybe obvious question where the answer is obvious. So the auxiliary qubits, they are used in order to cool one of the degree of freedom of the system. And why cannot you cool this degree of freedom instead of using an auxiliary qubit to cool it?
So I have a many-body system, which means I really have many degrees of freedom. Yeah. So not just one. But all these degrees of freedom are coupled. So it's like, that's why I presented first this steering protocol where you have a local refrigerator that takes out the excitations from the system, but then you have coherent interactions in the system that propagate the excitations to where the refrigerator sits. So I'm not sure I understand the question. I don't have a single degree of freedom. I have many degrees of freedom and they are coupled.
Yeah, but when you couple the auxiliary qubits to this degree of freedom, it cools the ones, like it interact with one of the degree of freedom of the bath. So then it's kind of cooling this degree of freedom of the, not of the bath, of the system. So it's kind of cooling this degree of freedom of the many-body system. So then...
No, it doesn't, because, and sorry for jumping in, but this is the reason why we need long interaction times. So the interaction time with the meter should be long enough that the system really undergoes internal dynamics. So this timescale is then set by the internal interactions that make sure that you are not just talking locally to a single site, but you're talking to a site which is part of a many-body system.
Okay, thank you.
Hi, thank you for an amazing talk. So I wanted to ask, like, if instead of so you said like, okay, you need a long interaction time between the auxiliary qubit and the system. But if you, like, instead of using qubits or like qubits with like higher dimension, does the interaction time decrease, do you think? Because there are more degrees of freedom where the energy can dissociate or something.
Not really. I mean, if you could, typically you just, well, maybe you're increasing your chances of hitting the right transition, but then also you have to think about the coupling. In the end, there is only, you cool whenever you have a resonant transition. So the transition of your meter is resonant to a transition that you want to cool. And even if you have a QDIT, it will only be one transition in the QDIT that will be resonant. So maybe you're increasing the efficiency a little bit, because if you have two transitions and you are able to couple both, then you double your chance. But it's just a factor. It's not going to be a huge difference at the price of making the interaction more complicated.
Okay, thank you.
Mm-hmm.
Thank you for your talk. I wanted to ask you, if you were to go for the protocol where you need three-body interactions, is there a platform that you think it would be straightforward to implement, or where you could generate these three-body interactions more naturally? So
people know how to engineer three-body interactions, but it always occurs an overhead. So typically what you do is you have only two-body interactions, and then you integrate out. You have like 3 degrees of freedom that are coupled by two-body interactions. You integrate out one of them and you get an effective three-body interaction.
Okay.
So it is known, but it comes with a substantial overhead, and it always comes not, so you never just get the desired three-body interaction. You always get also two-body interactions.
Mm-hmm.
So this is something that, but I think is more relevant for error correction. We have a paper on this, but not so much for the cooling here.
Okay, thank you.
Hi, thank you for a very interesting talk. I have like 2 small questions. First one is, what would all the conclusions stay the same if we assume that, let's say, in 5% of the cases the cooling qubit is actually excited, because you anyway need to prepare it in the ground state? And second question is, like, do we need to, like, to make it resonant? We need some knowledge about the system.
Okay, so let me start with the second question first. So the idea here is, since we sample the splitting, right? So we have a distribution which is either a flat distribution or a Gaussian, that is where the center is at 0 frequency. So whenever we prepare a meter, we draw a frequency from this distribution, and we adjust the meter to this frequency, and then we couple it. So that's why eventually we will hit resonances. And the second question was, if there is an error, of course, there is no zero temperature bath in reality. And the temperature of the bath, what I'm discussing here is essentially thermalization. Right? So if I have a finite temperature on my cold bath, I will thermalize my system to this temperature.
Hi, thanks again for the talk. I have one question or 2 questions. You said that implementing this just one interaction with the system was in order not to engineer a too complicated interaction. I was wondering if you thought about interacting with a system in more than one point. I mean, not n scaling, but maybe with a lower function, lower than n, for example, I don't know, square root of n or something. And if maybe if you do it regularly, you are hitting the spot where you are because of the symmetries of the system, but also randomizing where you put the interactions. If the
So yes, we have thought about it, and we actually discuss it in the paper on the steering. I didn't go into too much depth here, But yeah, so you can think of cooling a single link as the extreme dilute limit. That's why also we call it dilute cooling. But you can, so we don't want to scale, we don't want to have as many fridges as we have links, but you can say I cool every 10th link, or I randomize how, yeah, exactly. No, these variations are possible and probably also useful if you really want to go to large systems and have a
And do you know if
scale.
that makes the cooling time better or not?
Yes,
Is
it
that-
does, of course.
Okay.
Yeah.
Thanks for the nice talk. So I wonder if this kind of protocol kind of compared with the simulated annealing, because in the metropolis acceptance rules, like you just do local perturbation of your system, like fleet per spin, and then you calculate if the energy decrease, you accept it, or if the energy not it increase, then you accept it with probabilities. So I wonder if this kind of unlocks to that local interaction between your system and ancilla.
I don't know yet. We have been thinking about it because, you know, we call our auxiliaries meters.
Yeah.
And it would be very easy in the protocol to check if we have a click or no click after we disconnect the meter. But making use of this information is not trivial. So we haven't given up completely, but we have been scratching our heads on this for quite some time, and I don't have the definite answer yet.
Okay, I see. Thank you.
Oh, hi. Thanks for the nice talk. So I'll ask something more of like foundational questions. This reminds me of like the energy, time, and control complexity trade-off. But then I think in their setting, everything you assume you know something about the system. And then we bring out a nice point about agnostic being like the information about the system is not free. And do you think, can you like integrate this element into those trade-off and like come up with the new cooling bounds for that?
I think this is an extremely nice suggestion, but maybe somebody who knows more about this energy complexity trade-off should do it rather than me, because I'm really not an expert. But if anybody is interested, I'd be super happy to talk about it.
Okay, thanks.
Okay, any more? One more quick question, if...
I do. So I really like the idea of agnostic cooling protocol, and this reminds me of what we study in our group here at ICFO of Quantum Information Theory. We recently tried to approach many-body physics from the quantum information diagnostic perspective. So I was wondering if there is any way you can certify that your state is close to the ground state, treating it as a black box or as much as you can. Or if that would be interesting also.
It's definitely interesting. I have thought about it, but not enough to say anything which is not completely vague.
Okay.
But it's
so
definitely an
I will
interesting
approach
direction.
you
Yes.
now.
Okay, so let's thank Christiane again.